So I stuff that in there, and I'm now in a position to find the boil-up, provided I know something. And so what do I get for the boil-up? I get for the boil-up in case 2, minus B0, xd minus xb0. So far, so good. Integral from xb0 to xb. I must have an r plus 1 laying around. I must have an xd minus xb squared, and I must have a dxb. Okay. Well, xb is, of course, a dummy variable of integration. xd is a constant. xb goes with dxb. All this stuff is known. I need to find r. So let us do the r construction. Then we've got everything we need to make a choice. So what do I? Under the assumptions that we've been making, this might be the xd you're shooting for. And at that xd, you can take a look at r. Here's a line of slope r over r plus 1. You can take a look at another r. Here's a different r over r plus 1, and so on. You can put the equilibrium curve in wherever it is, and you can say, okay, at this r, I'll do it for 2 stages and a reboil. That's the xp. At this r, that's the xp. So I can map out a sequence of r's, get the corresponding xb's. That gives me r as a function of xp. I can perform this integration, and I get the boil-up. Now, one of the things a person might do is he might say, set the boil-ups equal. No. First thing you might do, most obvious thing to do, is just calculate the boil-ups. Find boil-up 1 and boil-up 2, and take the one with the least boil-up. It'll cost you the least heat. So that would make your choice for you. However, sometimes the calculation gets a little touchy, because even though you might be able to make the product specifications at a given r, you might not be able to make them when you're increasing r. So the best thing to do probably when you're making, and of course if you can't make it in case 2, then case 2 loses automatically. So maybe the easiest thing to do is to set the boil-up in 2 equal to the boil-up in 1, calculate xp, calculate the recovery, and make the choice on the basis of recoveries. Choose the one with the greatest recovery. So that's how that problem goes. Now, so this is, okay. So there's a lot of graphical work in doing these problems. But in every step you can see what's going on because you're actually drawing the picture. However, sometimes you can get away with a little murder. And suppose I got a problem like this. I might approximate this equilibrium with a straight line, which might keep me in the game in a region like so. So if my problem is at the dilute end, if I am at the dilute end, I might just write y equals mx. M is the slope of the equilibrium line at the bottom. So m is really alpha at x equal to 0. Now, I can probably get away with no graphical work. So we might see how this goes. Let us suppose we start with a reboiler at one stage. Now, I'm back to the case of constant R right now, but this will work for either case. I'm back to the case of constant R. And what I would like to know is, I need xd as a function of xp. So I begin by saying let n equal to 1. So I have stage 1 here, xd coming back, xd going off, xd going out. This x1 coming off of here, this yb coming off of here, xb is currently in the pot. And I begin by saying something like this: x1 equals xd divided by m. I want yb. yb is equal to r over r plus 1 x1 plus 1 over r plus 1 xd. I put x1 in there. I get r over r plus 1 times 1 over m plus 1 over r plus 1 xd. Now, xb is yb over m, so I have my first result. For n equal to 1, I'm going to write xb is 1 over m, r over r plus 1, 1 over m, 1 over r plus 1, xd. This is how xd and xb go together. I will simply write this as xb equals some factor c for 1 and r xd. I will go to my equation that I have to integrate, which is log b over b0 equals the integral from xb0 to xb of dxb over xd minus xb. And I will see that this is something like 1 over, xd is 1 over c, 1 over c1 of r minus 1 log of xb over xb0. So this is my formula then, and I've got a formula where all the variables are playing their known roles. The 1 stands for the number of stages, the R stands for the reflux ratio you're running. Suppose I do 2 stages. What do you reckon I'm going to do? If I do 2 stages, I'm going to do the very same thing. So I'm going to continue the argument, and I'm going to write in the end xb equals c2 of r xd. Yeah.
What is m?
It's the slope of the equilibrium curve at x1 equals 0. It's a distribution ratio. So when things are dilute, they're not complicated. I haven't even got the curvature of this thing into the game yet. So but you can look at here, do this. Write y equals alpha x over 1 plus alpha minus 1x. That's true whether alpha is constant or not. It's just that alpha is not constant. You can't make much use of it. But for x small, this is basically alpha at x equal to 0 times x, which I've chosen to call mx, simply because I've always called distribution ratios m or k or something like that. Okay, so that's what it is. Take the slope of that line. You've got the distribution ratio at very dilute case. You might get away with this up to, well, I don't know, maybe up to 20% or so. It's hard to say. But it's so cheap that you'd be crazy not to use it if it's close. So you can go find this C2 by the same argument we were doing there, and in general, you might write XB equals Cn of R XD. And here is where the R and the N plays its role. The integration then always integrates into a log. You got something down here. So if you know where the process ends, and you evaluate this and you evaluate this, this becomes an equation for Cn of R. If you know N, you calculate R. If you know R, you calculate N. So everything goes very smoothly as long as you're dialed. Now, we are going to, there's still some things on stage-wise that are interesting to do, but just to make sure we get where I might want to get to, we'll move on to packed columns. A packed column is something like this. Packed columns. Now, I believe on pages about 500 to about 550, you'll find King discussing how you deal with the transport of solute. And on about 550, roughly speaking, to 600, roughly speaking, you'll see he's talking about designing packed columns or predicting what they do. There's a lot of complications in this that are almost unnecessary, but I thought, well, let me draw a picture of what the problem is. The problem is this. I might have a gas stream here coming in at a flow rate V and a composition Y. I might have a liquid stream coming in, and these probably should be subscripted with an N. And I might have a liquid stream coming in at a mole fraction X and a flow rate L subscripted with an N. This, for example, could be water. This, for example, could be ammonia in air. So it may be that my solute is ammonia, or a lot of other things. My two solvents are air and water in this picture. What happens is this stream flows down, this stream flows up, and we try and make these streams contact one another by loading this column up with packing. So we put a little packing in here, put a little packing in here, put a little packing in here, put a little packing in here. Then the liquid kind of trickles down over the packing, and the liquid's trickling down over the packing, and the air is blowing up through here, and so you got a piece of packing here with a liquid film on it. You got air flowing past, they're exchanging mass, and we will probably introduce a notation that says something like A equals the area of contact per unit volume of the column. Okay, now, what is our job? Our job is to decide how fast ammonia is leaving this phase and entering this phase. So the air and ammonia are flowing up here. The ammonia is leaving the air, coming in here. Finally, you take a V and a Y out up here, and you take an X and an L out down here. And you might want to predict what these compositions are. You might want to predict how high the column ought to be to make a certain separation and so on. Now we've got a lot of work ahead of us. However, the main idea is, and I'm sure you will just absolutely love this, you'll probably stand up and clap. We have to write differential equations. Okay, and we gotta solve them. So I thought we would start by reviewing an old problem that you're supposed to know how to do, but which I think you may be quite confused by because I've seen what goes on out in the lab. So I thought I would review one of your favorite problems of all time. Problem where you've had to write differential equations. Solve them? Yeah. So what do you reckon it is? You bet. Hot damn. We're making progress. A double pipe heat exchanger. Now, I want to say something about this double pipe heat exchanger. We're going to get some results, but the results are loaded with assumptions.
Are you talking about like a concentric pipe?
Hmm?
Like a concentric tube?
I'm going to draw a picture here shortly,
Okay.
but that's exactly right. So we're loaded with assumptions. But I thought I'd run through this argument because we're going to make this same argument again. And I want you to remember where it came from. So we have this inner pipe, and we have an outside pipe, and we decide to measure Z from here. Here's Z equal to 0. Here's Z equal to L, the end of the exchanger. Here I am bringing in the pipe fluid at Tn. Here I am bringing in the outer pipe fluid at Tn, say star. Here I am. One of these is hot, one of them is cold. Heat's transferring as we go along. And I'd like to know, given the ends, given the length of the exchanger, and so on and so forth, what the T outs are. Now, I'm going to say this now, and then I'll say it when we're done. This formula we're going to get applies only strictly to the double pipe. You will see a logarithm appear. I do not want you guys, if you take first lab in the fall, to come use the log formula for other heat exchangers with different geometries without a lot of comment. This is the only exchanger for which, even with these assumptions, I can get a form with a log in it. That's the first thing. Secondly, there's another thing, and this is really important. When I get this done, I have a formula. I don't want you to write a report in the fall and tell me there's something called LMT, that's bullshit, and I don't want you to tell me there's something called epsilon NTU, also bullshit. Do not mention those words or you go down the tubes. Both of those are what we're going to do here. They're the same. They're just stupid ways of arranging the problem. So let us do the heat transfer problem, and what do we have to do? We have to write a couple of differential equations, so let us do that. But first, we cheat a little bit, and we say, there's something called a heat transfer coefficient, H say, which is going to tell us how fast heat transfers from, say, T average to T wall. And there's going to be another heat transfer coefficient on the other side, which is going to tell me how fast heat transfers from T average to T wall. And then I'm going to try and put these two H's together some way and get something called U, which is going to tell me how heat transfers from T average to T average. Okay, so right off the bat, this brings back great old memories, right?